Alright, this video gonna be interesting because in this video we'll store around 100 gigs of storage at just $2. That is, it is even cheaper than the hard disk or the external hard disk available on the market. So that is the power of object storage in AWS. Also, we'll be understanding the different lifecycle policies or the different tiers here. So before coming to this architecture diagram, how it works, let's first understand the basics of storage class, because this is the prerequisite which you need to know. Otherwise, the lifecycle policy, which is this diagram, would be a bit difficult to understand. So let's go through the basics. You got to remember, by default, whenever we upload an object or file in AWS in S3, it is by default in S3 standard tier, which is by default the costliest option. Why is it costly? Because we are frequently accessing the data. The concept goes something like that: the more frequently or more fast you access the data, the more costlier tier it will be. On the other hand, if we are not accessing the data, that is, it's a cold storage, also known as Glacier in S3. That is, if you want to just retain the data for, let's say, 5 years, 10 years, based upon the compliance requirement of any business or company, then we use Glacier. So it is just the opposite of standard tier. So here we are not retrieving the data, but we are just simply storing the data. We'll come to the Glacier. It's very interesting because we'll store in $2 100,000 gigs of data, that is around 1 terabyte. Let's understand the second important topic, that is intelligent tiering. Intelligent tiering is another important concept with regard to storage class, because it can store the data for unknown or changing access patterns. What do I mean by changing access patterns? Let's say I don't know whether a file or the object present in S3 is accessed in 10 days, 20 days, or 1 year maybe. We are not aware. Amazon S3, what it uses in intelligent tiering, that it will automatically know which tier to move. As mentioned, there are many tiers option as mentioned here in the bottom: standard, Glacier, infrequent access. In which tier it will be the cost effective solution, intelligent tiering does it automatically by using machine learning or AI, what you can also understand. You got to understand the basic concepts. Just remember, standard S3 standard is used for frequently accessed data. That is, it is a kind of hot storage. Second important point is intelligent tiering. When we don't know the access patterns, then we use intelligent tiering. And the third important concept is deep Glacier archive. It is the lowest cost storage class. That is, it will be the most pocket friendly option to store the files or the object in S3, right? So just remember the three important points. Though there are other storage classes as mentioned here, like S3 Express, One Zone, infrequent access, you can have a read at this, but in the interest of any AWS certification or any kind of data architect in real life as well, these three will always come in handy. Better to remember few things rather than remembering everything and confusing later, right? So let's now dive into the architecture. Alright, so the architecture diagram, as you might be seeing, that is, first is the S3 standard. After 35 days we can create a rule where it will be go to the standard infrequent access. The more right hand side if you look or go, the more cheaper option it will be. So Glacier, just remember it. Anything there are many variations of Glacier. If we look in the previous slide here, that Glacier instant retrieval, then S3 Glacier flexible retrieval, then Glacier Deep Archive. Just remember, whenever you see the term Glacier, think of cold storage, or when the data you don't want to access frequently, like it will be just like a just for storage purpose, just like you don't access or view all your videos or pictures on your computer, you just store them somewhere, like kind of memories. right? So just remember, Glacier is kind of that thing. And after 120 days or something, we can delete the object. So these days you see are not fixed. We can mention any number of days as per our compliance or the business needs. So I've just given one example to show how we can do it. And the interesting part is we'll see this in the demo itself, like how we can configure this thing. Not just theoretically I'll just implement as well practically to show you how we can achieve this in our real life project to save cost. Now that you have understood the lifecycle architecture, so let's also understand some of the important points. Just remember why we are doing the lifecycle management. The bottom line is we are trying to save cost. So that is what goes the point number one. Otherwise, people could have stored all the objects in standard tier, right? So that doesn't make sense. If we want to store cost, we need to do lifecycle management, or we need to move to the less costlier options like Glacier to save cost. Then comes point number two. These are nothing but some of the rules which you need to know, like what is the precedence, how the lifecycle configuration takes place, like permanent deletion takes precedence over transitions. Transitions, I mean to say this one, like from standard infrequent access to Glacier. These are called transitions. You need to know the hierarchy, what it follows, kind of board mass in maths, what we say. This is what you need to exactly know. But then again, like we don't need to mug them up or remember these things. It will come automatically as we do the hands-on. As mentioned, the important part is the standard S3 standard. You just got to know this thing, S3 standard. Then comes the next important thing is the intelligent tiering. That is, it automatically moves the data when the access patterns are unknown, right? So this is another important point. And the most or the last important point is the S3 Deep Glacier Archive. This is if you want to store cost, if you want to save cost, I mean. Let's see this in the cost calculator. I have already done my homework so that it shouldn't take time or we waste time doing this. See, 100 gigs per month, 1000 gigs per month, I mean, it costs just $2. And even we can mention the size of the object for 250. We can give even, let's say, 1000, that is, it will be 1 gigabyte file. If you are on an average the size of the files or the object, it will still cost around $2. It is very cheap compared to the market external hard disk or SSD if you want to store any kind of pictures or videos, just like for the memory sake or something. So you can utilize S3 Deep Glacier if you want to utilize the power of cloud. So let's now do some hands-on for the architecture diagram which we have shown. Alright, let's look at this question. So first we'll look at option A. Option A says migrate the servers to EC2 instances in Outpost and update the pipelines to use these EC2 instances. Using AWS Outpost and migrating to EC2 instances would require significant changes to the infrastructure and increase operational complexity. Hence incorrect. Let's move to option B. B says use the AMI to launch EC2 instances and update the network settings to connect to new EC2 instances. Creating a custom AMI for Apache Airflow and running it on EC2 instances still involves managing EC2 instances, which introduces operational overhead. And we need to minimize the amount of refactoring or kind of operational overhead, right? So let's remove this. Let's move to option C. Option C, if you look, the minimize the amount of refactoring. This specifically means or points out to Amazon managed workflows for Apache Airflow, which is a fully managed service for running Apache Airflow. So we'll park this. Let's move to option D. This is redesign the pipelines using AWS step functions and re-implement the SQL-based data quality checks as Python Lambda functions. AWS step functions and Lambda functions requires significant changes to the pipeline. Hence incorrect. We will lock option C as the correct answer. Alright, now so let's look at this question. We need to optimize the query performance as well as storage cost. Let's look at option A. A says .csv format compressed with zip. .csv is a row based format and not efficient for analytics. Hence incorrect. Let's move to option B. B says JSON format compressed with bzip2. JSON is row based and lacks the optimization provided by columnar formats. Hence incorrect. Let's move to option C. C says Apache Parquet format compressed with Snappy. Parquet is a columnar storage format which is significantly improves query performance for analytical workloads by enabling column pruning. Let's park this. We'll move to D. D says Apache Avro format compressed with LZO. Apache Avro we know is not optimized for query performance in Athena as Parquet, what we saw in option C. Since option C is better than option D, let's reject option D straight away and log C as the right answer. Alright, now so let's look at this question. This is all about new partitioning without scanning all directories and files in the table's location. Let's look at option A. If you look at option A, this option adds the new partition to the table without scanning all files and directories, which is what required, right, as per the question here. We'll park this. Let's move to option B. B says MSCK repair table transaction. MSCK repair table scans all the directories and files to update partitions, which is not efficient for this use case. Incorrect choice. Let's move to C. C says repair table transaction. Repair table is not a valid DDL statement in Amazon Athena. We'll eliminate this. Let's move to option D. So if you look at option D, alter table modify partition modifies existing partitions but doesn't add new ones. So it's incorrect for adding partitions. So we'll eliminate this. Let's lock option E as the right answer. Alright, now so let's look at a question which is about creating data pipelines to handle incoming files which is in .csv format, which users uploads to S3 bucket, and the size of each object is less than 120 MB. So let's look at the options now. Option A says develop a custom Python script and deploy it on Amazon EKS, that is Elastic Kubernetes Service Cluster. Managing an Elastic Kubernetes cluster can be more complex and costly. As per the question, we need most cost effective solution, right? So this is out. Let's move to option B. B says develop a PySpark ETL script and run it on an Amazon EMR, also known as Elastic MapReduce cluster. Running an EMR cluster can be again more expensive and overkill for the size of data, that is for 120 MB. We just have the size of 120 MB. So EMR this is not a like Hadoop case and all, so we don't need it. So wrong answer. Let's move to C. C says develop an AWS Glue PySpark job using Apache Spark for data transformation. Using Apache Spark for such small size can be unnecessary and more costly compared to using a simple Python shell job with Pandas library. So we'll eliminate option C. Let's move to D. D says develop an AWS Glue Python shell job using the Pandas library for data transformation. This option leverages AWS Glue, which is a fully managed ETL service we know, and also uses Pandas for transformation, which is efficient for the size, that is 120 MB of data. That looks good. We'll lock D as the right answer. Okay, so we got this time a really interesting question. This is all about dynamically redacting PIA. So we have done hands-on similar to this. So this should be a piece of cake. right? So let's look at option A. A says set up an S3 bucket policy to restrict access per application and create multiple dataset copies with different redaction levels for each app. Multiple dataset copies lead to increased operational overhead and complexity. Incorrect choice. Let's move to option B. B says use an S3 object lambda endpoint to dynamically redact PI when data is accessed based on the application's needs. S3 object lambda dynamically modifies data during access, allowing for efficient on-the-fly redaction based on application needs. So this looks good. Let's move to option C. C says use AWS Glue to transform the data for each app, creating separate dataset copies with different redaction levels. AWS Glue requires additional processing and management, which adds complexity. As per the question, we need to minimize operational overhead as well, right? So this is out. Let's move to D. D says set up an API gateway with custom authorization to fetch and redact PII data via an API call. API gateway introduces unnecessary complexity for this use case, what we have as per the question, compared to S3 object lambda, which is option B. Since option B is better than option D, let's reject D and lock B as the right answer. All right, now so let's look at this question. This is about detecting data schema. Looks good because this is also easy question because we have done the similar hands-on. Let's look at option A. A says use Amazon EMR to detect the schema and process the data using Apache Spark, then load it into the S3 bucket. Amazon EMR requires more management overhead compared to AWS Glue. Hence incorrect. Let's move to B. B uses Glue to automatically detect the schema, transform the data and load it into the S3 bucket. AWS Glue we know is a fully managed ETL service which can automatically detect schemas, transform data and load it into S3. Let's park this. Let's move to option C. C says create a PySpark program in AWS Lambda to detect the schema and process the data and load it into the S3 bucket. AWS Lambda is not well suited for processing large datasets due to limitations in execution time and memory. We'll reject this. Let's move to option D. D says create a stored procedure in Amazon Redshift to detect the schema, transform the data and load it into a Redshift spectrum table, then access the data from S3. Amazon Redshift and Redshift Spectrum are better suited for analytics, not ETL, what we have as per the question. Therefore, D is out. Let's lock option B as the right answer. Alrighty, so we got one question related to Hadoop big data. Interesting, and we will find this type of situation in real life projects as well, because as a data engineer, we need to handle big data workloads as well. Let's look at option A. A says if we look at option A, this option is most cost effective as it leverages AWS data migration service to migrate the Hive metastore to Amazon S3 and AWS Glue to scan and produce the data catalog, which aligns with the requirement of a serverless solution. We'll park this. Let's move to B. If you look at option B, though it uses AWS Glue, it involves additional overhead by setting up Hive metastore, which is this in Amazon EMR. That's why you will reject this. Let's move to option C. So if we look at option C, adding Amazon Aurora MySQL increases complexity and cost as well. So we need to minimize the cost, or we are looking for most cost effective solution. That's why using Amazon Aurora MySQL won't help in this case. We will reject this. Let's move to option D. If you look at option D, setting up a new Hive metastore in EMR adds extra steps and is not a serverless solution. As per the question, we need a serverless solution, right? So this is incorrect. We'll reject this and lock option A as the right answer. Alrighty, so this is all about Amazon Redshift serverless. We'll look at option A. Option A, if you look, while this can work, this will introduce additional steps, that is Kinesis Firehose. This is incorrect. Let's now move to option B. B says leverage Amazon Redshift native streaming ingestion feature to for direct data loading. Amazon Redshift's streaming ingestion capabilities supports real-time data streaming to Redshift. Looks good. We'll park this. Let's move to option C. C says store the data in Amazon S3 and use the copy command to load it into Amazon Redshift. This approach requires batch processing using the copy command, which is less suited for real-time analytics compared to Redshift's streaming ingestion feature. We'll eliminate this. Let's move to D. D says utilize Amazon Aurora's zero ETL integration with Amazon Redshift to load data. The integration is for Aurora and Redshift, which is not designed for real-time streaming for external sources like Kinesis. Therefore, we'll reject option D and lock option B as the right answer. Let's bring the heat to the snow. So we got to select an option which should minimize operational overhead. If you look at option A, while AWS Glue notebooks with Spark introduces more complexity and management compared to using Athena with Glue's data catalog. So for now, this combination, especially Apache Spark job using AWS Glue notebook, is incorrect because it would increase operational overhead. Let's remove this. Let's move to option B. B says set up an AWS Glue crawler to catalog the data in S3. Looks good because Glue works well with S3 for the data catalog and all. And then use Amazon Athena to run SQL queries. This is again a great combination because Athena is meant for querying data. Then it says that compute the number of distinct customers. Looks good because AWS Glue crawler can automatically create a data catalog from the S3 object or the files present there, and then Athena can easily run SQL queries on the catalog items or catalog data. Let's park this. We'll move to option C. C says run an Apache Spark job in Amazon EMR serverless to process the file and compute the number of distinct customers. Using EMR serverless also requires setting up and managing Spark jobs, which will increase operational overhead. We'll reject this. Let's move to D. D says use AWS Glue Data Brew to create a data recipe that applies the count distinct aggregation function to calculate the number of distinct customers. AWS Glue Data Brew is a powerful tool for data preparation, but its capabilities are best suited for smaller interactive workflows. For now, as per the requirement, this is out. We'll lock option B as the right answer. Alright, again we got to select a solution with least operational overhead, or which should minimize the operational overhead. Let's look at option A. It says use Amazon step functions to automate pausing and resuming the Redshift cluster for monthly tasks. Step functions require managing a provisioned Redshift cluster, adding operational overhead. Therefore, wrong choice. Let's move to option B. B says use Amazon Redshift serverless to handle the analytics workload automatically without needing cluster management. Amazon Redshift serverless automatically manages the workload without manual cluster management, offering the least operational overhead. Looks good. We'll park this. Let's move to option C. C says use the AWS CLI to automate the execution and management of the Redshift's cluster each month. AWS CLI still requires manual cluster management and is less automated. So this is again out. Let's move to D. D says use AWS CloudFormation templates to automate Redshift cluster setup and management for monthly tasks. CloudFormation automates infrastructure but still requires cluster management, adding complexity, right? So cluster management will increase the complexity, which is again the goal of the equation, that is we need the least operational overhead. That being said, option D is out. We'll lock option B as the right answer. So please don't go away. Let's meet in next part of this series.